Okay, welcome to Chapter 12 of Physics 201. Here we're going to be discussing waves, and in this particular segment, we're going to be looking over sections 12.1 through 12.4. Now, to give you a general summary here as to what it is we're going to be tackling, a mechanical wave is going to be any disturbance from an equilibrium condition that propagates from one region of space to another through some material called a medium. And the medium could be air, it could be earth, what have you. In a periodic wave, the motion of each particle of the medium is periodic. The period, t, frequency, f, wavelength, lambda, and wave speed, v, are all going to be related. And you can see the relationship here. The velocity is going to be equal to the wavelength times the frequency, which is going to be the same thing as the wavelength divided by the period. So for a string with mass per unit length mu and tension F sub t, speed of the transverse wave is going to be equal to the square root of the tension divided by the mass per unit length. Also, simple harmonic oscillation drives the sinusoidal transverse wave. So think about a spring that's moving back and spring that is moving a string and it's bouncing up and down. You can see the wavelength as it goes from peak to peak. The amplitude is going to be the amount of separation, maximum amount of separation from an x-axis. The velocity of the wave is, in this case, going to be pointed this way as the wave is moving this way. And each particle on the rope is going to oscillate in a simple harmonic motion. So let's take a look at these sections individually, and let's kind of see what they have to talk about. Electromagnetic waves, such as radio and light waves, don't require a medium and are not considered to be mechanical waves. A mechanical wave travels through its medium, and the particles that make up the medium undergo displacements of various kinds. The speed of travel of a wave depends on the mechanical properties of the medium. Some waves are considered to be periodic, which means that the particles of the medium undergo periodic motion during wave propagation. If the motion of each particle is simple harmonic, it is the same thing as saying it's a sinusoidal function of time, and it's also called a sinusoidal wave. So you can see here in this figure, we've got three examples of mechanical waves. And this first one, the medium is a stretched rope. If we give the left end a small up and down wiggle, up and down, then the resulting pulse wave travels down the length of the rope, and successive sections of rope undergo the same up and down motion that we gave to the end, but at later times. Because the displacements of the particles in the medium are perpendicular, in other words, the rope is going to move up and down as opposed to with a wave, which is actually moving out to the right. This type of wave is going to be called a transverse wave. Now, we do have other types of waves here, which we're going to get into. In this particular figure, 12.2b, the medium is a liquid or gas in a tube with a rigid wall at the right end and a movable piston at the left end. If we give the piston a back and forth motion, a displacement and a pressure fluctuation travel down the length of the medium. This time, the particles of the medium move back and forth parallel to the wave direction, and this is going to be considered longitudinal because the motion of the wave is going to be in the same dimension as the movement of the particles of the field. So in this figure right here, the medium is water in a trough. When we move the flat board here at the end, back and forth, the disturbance travels down the length of the trough. In this case, the displacements of the water particles are found to have both longitudinal as well as transverse components. And this is the familiar waves of oceans and lakes are of this type. They're most often generated by wind moving over the water's surface. Earthquake waves have both longitudinal and transverse displacements. The longitudinal component travels faster and so gives you advanced warning of the arrival of the more destructive transverse components. And this is the kind of thing that will tell you things that will trigger tsunami warnings. For each one of these cases, there's going to be an equilibrium state. It depends on the type of situation that you're in. When the rope is at rest, that's going to be stretched out along a straight line. That's going to be considered at rest for the fluid in the tube. It is at a state of rest with uniform pressure, as for water in a trough, if it's at a smooth surface. The wave is going to be a disturbance from that state. In each case, there are forces that tend to restore the system to its equilibrium position when it's displaced. In each of these situations, the medium as a whole does not travel through space. Its individual particles go back and undergo back and forth motions around their equilibrium positions. So what does travel is the pattern of the wave disturbance. So to set any of these systems in motion, we have to put energy in by doing mechanical work on the system. The wave motion transports this energy from one region of the medium to the other. So waves transport energy, but not the matter, from one region to another. And you can see that because the particles don't really have a lot of total movement or net movement in one direction or the other, but the energy does. So the disturbance is found to propagate with a definite speed through the medium. The speed is called the speed of propagation, or just simply the wave speed. So that's section 12.1. Now let's take a look here at section 12.2. So we're going to be looking at transverse waves here, and we've got our stretched rope. It's attached to this mechanism that is moving up and down. So what we're going to do is we're going to take one end of it and we're going to give it a simple up and down shake. And that wave pulse that is created travels the length of the rope. The tension in the rope restores the rope's straight line shape once the wiggle has passed. A more interesting situation develops when we give the free end of the rope a repetitive or periodic motion. So we're going to describe this motion with amplitude A, frequency F, and period T. We know that the frequency is going to be 1 over the period, which is the same as the angular frequency divided by 2 pi. A continuous succession of transverse sinusoidal waves then advances along. So you can see the crest here, there's the trough. The amplitude is the distance away from the axis that we're measuring. The motion of the wave is in this direction. So this, we've got the simple harmonic motion of this, and it generates a sinusoidal wave in the rope. Each particle in the rope exhibits the same harmonic motion as the spring and mass. And the amplitude of the wave is the amplitude of this motion. So if you were to take this wave generating oscillator, and if you were to time it at certain fractions of a period, you can see here that it'll start out here at a distance y away, whatever the amplitude is. And we're going to look at these three parts on the rope. As we go through, we can see how the position of these points on the rope change. But you can see how the same basic shape of the wave starts to advance. And it's going to advance by a wavelength. You'll notice here you had the wavelength here. And by the time you end the period, it's going to be over here. And in the meantime, all of these purple dots on the rope are going to be bouncing up and down. So again, we've seen in the summary how to summarize the speed of this particular wave. This equation right here is going to be true for any wave, including those that are not mechanical. In point of fact, we actually use this for a speed of light, which does not require a medium. For many waves, the velocity is determined by the properties of the medium. So if the wavelength changes, then the frequency of the wave must also change in order to keep that constant. So if that changes, that must change in order to keep that constant. So if we look at a longitudinal wave, we've got a plunger here, which is going to be moving in and out in simple harmonic motion. The forward motion is going to create a compression, and you've got a compression followed by an expansion, followed by a compression, followed by an expansion. So the wavelength in this particular case is going to be the points, the highest points of compression here, the distance in between those. The wave speed, again, is going to be in the same direction as the movement of the particles here in this plunger. So again, if we look at a chart of the motion of these particular particles, and remember they're moving left to right, as we look at the period as it goes through, and the plunger eventually pushes in, pulls back out, and then comes back, we can see how these particles move. And again, we can see the wave as it advances by one period. So there are some more exercises here in 12.2 that I would definitely encourage you to work through. Now we're going to move on to section 12.3. So in 12.3, what we're going to be looking at here is that the speed of propagation of a wave depends on the mechanical properties of the medium. So for transverse waves on a rope, these properties are the rope's tension as well as the mass. Intuition suggests that increasing the tension should increase the restoring forces that tend to straighten the rope when it is disturbed, and thus increase the wave speed. So we might also guess that increasing the rope's mass should make the motion more sluggish and decrease the speed. So both of these expectations are confirmed by more detailed analysis. Basically what that means is, yeah, we checked it out and it's fine. The inertial property of the rope is best described not just by the mass, which depends on the length L, but also by the mass per unit length. In other words, we would take M divided by L, and that gives us a density of some sort. So we're going to denote the tension of the rope by this. So essentially what we're saying here is that the velocity of the transverse wave in a rope under the tension, it's going to be directly proportional to the tension. It's going to be inversely proportional to the mass per unit length. And then you take the square root of those and you actually have your velocity. Obviously the force is going to be measured in newtons, and the mass per unit length is going to be kilogram divided by meters. Again, you got some more examples here. So now let's move on to 12.4. All right. So we've described several characteristics of periodic waves using the concept of wave speed, period, frequency, and wavelength. But maybe we can come up with a more detailed description of the positions and motions of individual particles of the medium at particular times. So let's look at the waves on a stretched string. If we ignore the sag of the string due to gravity, then the equilibrium position of the string is along a straight line. We take this to be basically the x-axis of the coordinate system. That's everything that we've come to see up to this point. So waves on a string are going to be considered to be transverse. So during wave motion, a particle with equilibrium position x is displaced some distance y in the direction perpendicular. The value of y depends on which particle we're talking about. In other words, where are we over here? Y is going to depend on where we are away from the origin. And also on the time t. So y is going to be a function of both where we are this way and at what time we're looking at this. If we know this function for a particular wave motion, we can use it to find the displacement of any particle at any time. Here's a list of all the speeds of sound. So if we go through and if we do that, then we can say that y is equal to a times the sine of omega t, or a times the sine of 2 pi ft. The resulting wave disturbance travels with speed v from x is equal to 0 to all the points to the right. Every such point undergoes simple harmonic motion with the same amplitude and frequency as the endpoint. But the motion of each point has a time delay, x divided by v, equal to the time required for a point on the wave shape to travel. So thus, the motion of point x at time t is the same as the motion of point x is equal to 0 at the earlier time t minus x over v. Therefore, we can find the displacement of any point x at any time t simply by replacing t in equation 12.3, right here, with this. So when you go through and you rewrite it like that, that's what you come up with. So basically, if you take, knowing that the period here is 1 over f, so if you make a switch here, and that the wavelength is velocity divided by the frequency, then you can make a replacement here, and it can end up looking like this. So depending on what you know and what you can substitute in, you've got yourself an equation where you can find where the point is in the y direction at any particular time. So that's the first 4 sections of chapter 12, and play around with some of the examples here, and I think you might find this interesting, I think.